So getting into the fine mesh models, we'll basically be dealing with two types, the top-down analysis and the embedded analysis. The fine mesh creation that we'll be doing is from within Maestro. You could also create your fine mesh models outside and stitch them in, but you would have to, I think, manually map any of the loads that are contained in the model onto those fine mesh portions. If you had, say, we have a couple areas of deck where we have cargo masses, we have tank pressures, things like that. So the easiest way of doing this is to use the Maestro interface to create a group and then use the automatic refinement in Maestro for the fine mesh. What we'll need to create are some general groups, and once we have the general groups created, when we right-click, we'll use the refine command to generate the fine mesh model. So we'll start off with just creating a couple of small areas of deck plating. So we'll just create a small general group from the corner up here as a test case so we can run some samples on for generating the fine mesh. So we'll generate general group. We'll include the beams, some shell plate, and we'll get part of the deck as well. Now we could select any portion of the model that we wanted, and we could have terminated this at a frame boundary, at a bulkhead boundary, and so forth, but it's probably preferred to break it in the region between the frames as opposed to on the frames. It would work either way, but this is a little cleaner to break it sort of mid-span between the frames. And when we create that group, we'll also create just a single element for doing a couple tests later to see how the meshing options select sizes. So we just created general groups 3 and 4. I'm going to rename this to edge, and we'll call this one single panel. So to open the dialog, we just click on any general group and use the refine option. So it'll use the same name by default for our fine mesh module that it creates in the parts tree, but we can rename it here if we were going to, say, run several options. Maybe we want to check different connections of the deck frame to the side shell frame. So we could append onto this name to describe all the various options we want to run. Now, since we're refining the model, depending on how much we refine it, we may want to change the nodal tolerance. So this is sort of an override of the general nodal tolerance for the global model to just be applied on the fine mesh model. So if we were to get into some very small meshes in there, we may need to bump that down from a millimeter to something smaller. Typically, you probably would need to. It would all depend on what the mesh tolerance is on the global and exactly how fine you want to get with this fine mesh model. The next option is simply where the origin of your fine mesh model is going to be. And we've dealt with the module dialog here where we have substructures and modules, and each one of them has a location associated with it. Typically, I think by default, it's going to use the global origin 000 for the default location of the origin of our fine mesh, but you can change that to anything else if you prefer. It's really mainly for editing. It won't affect the analysis or results. It's just a reference point for your model. So if you were to go in and query the location while editing, actually, I think when you query, it's going to give you the global coordinates anyway. This is just the origin if you needed to move your module around or for some other reason, but it's probably simplest just to keep the default and use the global origin. The next thing you'll want to know is what the refinement type is. We're basically going to be dealing with just the top-down and the embedded models. And the top-down model leaves your global model in its original state. It doesn't make any modifications to your global model at all. It creates these fine mesh modules as a sort of an overlapping portion of your global model. And the global model will be solved completely first, and then the edge boundaries from your fine mesh model, the global deformations will be imposed on your fine mesh model, and the fine mesh model will be analyzed. The other option is an embedded model, and in an embedded model, we're going to replace that portion of the global model and create a new fine mesh version that gets stitched in to the global model using those same R-splines that interpolate the displacements between the two modules. Some of these others, the Alps call and Procol, we won't be covering. For multiply, these other ones are more special case type options. The Alps call and Procol are for those modules. The multiply, I haven't used personally. I'm not sure what that one does. The one-to-one map, I believe, is for Nastran. If you wanted to, say, write out just a small portion of the model, you can use this option to, rather than actually defining the model, it does a one-to-one conversion where it takes that group and basically writes it out as a smaller group with the spline connections to a global model, so that when you write out the Nastran model, you can write out just that small piece of the model with all of the deformation imposed on it from, as well as any of the map loads from the global model, so that you could run the analysis in Nastran at the same resolution with the same element types from the Maestro model. The super element is for actually creating larger elements from the standard mesh, and the full model is a fairly new option where you essentially create one group that contains the entire model, and it's for doing a global refinement of your entire model in sort of an automatic fashion. And that's still in development, but it works fairly well at the moment. There is some manual cleanup required when you do the entire model, but it does work fairly well. The next area is the load control, and this grayed out option here, I don't know if this was ever fully implemented in Maestro, but in any case, it is not an active option, so you don't have to worry about this one. The other one, map loads, you will most likely always leave checked, but the option is here to remove the load. And basically, it's when you generate the fine mesh module, those elements contain any existing loads that we define. Say, if we were to make a fine mesh module that was on one of these areas where we had defined a cargo weight, or if it was on a tank boundary, there might be a pressure load from the contents of the tank, or on the submerged side shell, we've got hydrostatic pressure. This also, if you had used any of the pressure options on a plate, the appropriate portion of that load would get mapped to the fine mesh model, so that when it's run independent of the global model, those sort of loads that aren't on those boundary edges will be applied to the fine mesh model. The next item is the mesh control, and the upper one, the minimum length along non-stiffened edge, will basically control the mesh size on your fine mesh. And by minimum length, what it will do is, if you don't use the default, and I believe the default is to break up the nominal mesh element into 5 divisions, but you can specify a size. And what it will do is take that edge, divide by that length value that you give it, and figure out how many intervals will fit, and divide it into that many intervals. So if it isn't an exact number, it'll sort of make slightly larger elements so that the value that you specify will be a target, but the actual resulting value will be that value or slightly higher. This other option, minimum number of segments between stiffeners, is for if you have an internal stiffener layout. And don't know that it is currently editable. I think it is currently locked at 1. I don't know if there's a plan to change that. Right now, if you have a model that uses the stiffener layout, such as we had seen on some of the sample models, it'll convert those internal layouts to discrete stiffeners and put one quad element between. And to investigate this minimum length control, let's switch over to that single panel model. And we'll just use the defaults up above. And if we use the 0 for the default, we know that that one single deck panel that we created is a 1 meter by 1 meter panel. You can see it was meshed into a 5 by 5. So if we try that again, and instead of using the default, if we use 5, we should get a 4 by 5. And if we use something that doesn't divide exactly in there, such as, let's say, 4, we get a 2 by 2. Now we would still get the 2 by 2 if we use 0.5, but there should have been 2.5 in here, which obviously isn't an option. So it uses the two whole elements and just increases the size to fit the edge. And when you create any of these fine mesh models, you'll see there's an additional folder that's created under the general group that contains entries for each one of these meshes. It's actually converted these. When you do the refinement, it creates it here as a group, and then I think converts that basically sort of with the create module that it creates in the fine mesh portion of the tree here. And since this is a top-down, now as we'll see later, when you create an embedded mesh, because it's replacing part of the global model, it'll actually create that under the top portion, which contains your global model. In part, that's because when you go to do your runs, we can run when we analyze. Typically, we'll do the global and local FEA, but if your model does contain a fine mesh model, or more specifically, if you have a lot of fine mesh models in there, which would slow down your runtime, you may want to solve the global FEA model separately to see if things are working as expected on a global scale, make sure everything passes whatever checks are needed. And once you have a good design, then you can run the local FEA to evaluate all of those fine mesh options that you have in. Now, if we delete any of these fine mesh modules, they will automatically get deleted from the groups tree. Come back in here, we'll see that fine folder is now empty, although they were actually empty groups anyway. We'll go back to the deck edge module. And you can create as many top-down modules as you want. Once you create the embedded module, you're replacing part of the hull, so you're sort of locked into that one refined mesh option. But the next step is to tell it how you want to refine your beam element. And these are down below are the setting options for refining the various beams, whether they're girders, frames, or stiffeners. And by default, it'll do it by beam type. And as you may recall, when we're creating these beams, part of the definition is whether this beam element is going to be used as a stiffener, a frame, or a girder. And there's an entry in here for beam type. And even if you have the same size or an identical beam, if you define it to be used as a stiffener in some locations and as a frame in others, this setting is what's going to determine how these are evaluated when you're going to do the refinement. So by default, for frames and girders, it will use one quad element to model the web, and then the flange will be converted to a beam element. We also have the option of leaving the frames and girders as beam elements, in which case we don't have to worry about the flange anymore. If we are converting it to the quad element with a separate element for the flange, then we have the option of creating that flange either as a beam, which will be, I guess, centered on well, actually, I take that back. We were using T's, so the T's will have that flange centered on the beam for when it gets converted, as you'll see. But it can also be converted to a rod or to quad elements. And then the stiffener, by default, will convert to a beam, but you also have the same option where you can convert it to a quad and then model the flange separately as either a beam, quad, or quad. Now, the second option here is to determine whether it's a girder, frame, or stiffener by web height. And when you use the web height option, it's only going to apply to the deep beams, basically your girders and frames. And your stiffeners still have the same options for quads and beams. If we were to switch that to a quad, we can assign the flanges separately, but stiffeners will typically just be left as beams. Now, when we convert the deep beams, if we're using this option, the web is going to be converted to a quad, and then we have the three original options for the flange. So to test that, since we're doing the deck edge and we have, oh, actually we only have frames in there. Let's create another patch here, another general group that we can evaluate where we're going to have both a girder, a frame, and a stiffener. that'll be enough for the demo. So this one will use web height. Now we know our girders were 500 millimeters, although the web height is actually a little bit less than that. If you look up the actual beam sizes from a properties table, we can see that our 500 millimeter girder is actually about 464, and our 380 frame is only about 360. So we come in here to define that deck patch and do it by web height. If we give it a value of 0.4, something between the frame and girder, you can see that our 500 millimeter girder was converted to quads, but our frame, being only 360, remained a beam. Let's go back to the deck edge refinement here. And with these top-down models, we can create as many as we want since we're not replacing anything on the actual model. We'll just use all of the defaults for this first iteration. And the resulting fine mesh model, you can see it converted our deck frame and our side shell frame and connected them at the web. Maestro will attempt to do this. There are some cases where you may not get a clean conversion like this one seemed to get everything exactly as we wanted it. But in some cases, if you had different sizes of deck and side shell frames and they were intersecting at different angles, occasionally you may get a version where the frame will run up to the deck and this frame will run to the side shell as opposed to being blended in the corner here. Now, one of the nice things about the top-down fine meshes is that if we wanted to evaluate, say, multiple options for how these frames are going to connect, or with and without a radius fillet in this corner, and whether or not that radius is a piece of plate here and leave the flanges as they are and just weld a radius plate in this corner, or if we create a rounded corner here and run the flange around the rounded corner, or leave it squared like this and say run this flange to the side shell, or perhaps we use triangular brackets on either end to help transfer the load to the webs. So we could run multiple options of how these would be built. Each one could be its own separate top-down model. And we could have 4 or 5 different options here where Maestro would evaluate the global model and then run each of these various options of the fine mesh using the exact same displacements along the perimeter. And that gives a pretty good idea of exactly what all of those things are doing for our options. So let's create another. I'm not sure what will happen if we have a top-down deck edge and then we do the same with the embedded. I don't know if it'll destroy these or if it'll have a fine mesh model embedded and top-down models of the same thing. You can probably do that. It would be a little redundant, I guess. But the main difference between the two is that when you run the top-down model, the global model is solved first and completely independent of any of your fine mesh models. And the data for your fine mesh models is taken from the global model and imposed on the boundaries of the fine mesh. Whereas if you do an embedded model, it replaces this portion of the global model. And when you run the model, both the fine mesh and global are run at the same time and contribute to each other. So let's make a separate copy of this file. So we're going to save this one as what I'll do is delete the fine mesh groups we had created. And then we'll create the embedded version. And we'll just use the default here. When we come back into the parts tree, you can see instead of creating that separate fine mesh alongside the top level, it creates it inside the global model. So now if we view the model at the top level, we can see our embedded fine mesh, which is replaced. that portion of our